Hello and welcome to Graphics, Gears, and Wires. This is Henry, and today I'm going to take you through a build video I did of one of my new robots. It's a small robot. It's a test for something larger I'm building, and I wanted to share the process of actually putting it together. So this is a time lapse, and I'm going to go ahead and start it now, where you can just take a look at the whole project coming together, some of the things that I do to fit everything into a small space. And here I'm laying out, I print a template with the screw holes so I know where to drill, and I'm going ahead and just marking the box. That's a box I got from, I think, Michael's Arts and Crafts. It was like $4. And things like this are great little project boxes. They're wooden, so they're easy to screw into. You can get plastic project boxes at a lot of places. But I find them harder to work with unless you're going to use a lot of hot glue and drill a lot of holes. The wood boxes let me screw these components right in. Here I've got some 3D printed sonar brackets that I made for the front of the robot. And you can see they sit on the outside facing in on the robot. That's a design similar to what they do on the front of the Boston Dynamics dog robots. I've been playing with this design for some time, trying to get the best obstacle avoidance, and I find I catch more obstacles with crossing forward-facing sonars than I do with outward-facing sonars. So that's been kind of my go-to moving forward on robotics with sonar, trying to cross in front of the robot rather than point out like feelers from all sides. And here I'm just trying to work as precisely as I can to mount this tank tread kit that I bought. I got that on Amazon. It was probably about $45. The kit, honestly, not such great build quality. I had to make a lot of adjustments just to get it to work. There were a few places where there were washers missing, or a hole was too big, and the screw that was supposed to go through it would just go straight through. So I do not recommend those tank treads. I'm not even going to link to them, because this will be the only time I use them on this particular robot. Usually I build a larger drive system with DC motors and custom printed brackets. Here I wanted a fast solution because I wanted to start prototyping something on the Ross navigation stack. So here I'm just going to take everything apart. I was just fitting everything. Then I'm going to get the rest of the holes done. Alright, that's a better camera angle. So let's start threading wires through this box. And I probably should have made a bigger hole, because there's a lot of wires to go through. Each of the motors, I think, has 5 wires, and that controls forward and reverse direction. It controls the encoders. The encoders let you, if you don't know what a wheel encoder is, lets you know how many times a wheel has turned, and it lets you know that more reliably than doing something like trying to time it. A lot of times when you're building a robot like this, you'll find you'll put it together and it just doesn't want to go straight. And you'll discover at that point what wheel encoders are all about. At the end of the video, I'm going to show you the wheel encoders actually working, so you can see what I'm talking about. But it helps you to know that your robot has moved forward a certain amount of space. It doesn't solve the problem of things like sliding or something like that, where a wheel will turn but it won't actually move the robot because of lack of traction. There's a lot of things when you start building robots like this that you're going to use for autonomous navigation that you just don't think about until you start seeing them roll around and realizing, hey, he thinks he's going straight, but his left wheel's sliding a little bit on this surface. You'll also notice that 2 identical DC motors connected to the same battery a lot of times will turn at slightly different rates. So to compensate for that, you kind of throttle the amount of voltage you're giving those motors. And that's what the wheel encoders will help you do, is know that you've got them turning at the same rate. So here we're just going to get these sonars back on now that the wheels are on and they're no longer in the way. Now these sonars, I get them in packs on Amazon, and I find them to be kind of a delicate piece of equipment. I've not burned up a single Pi or Arduino just kind of screwing with it, but I've had a few of these that'll work, and then I'll take them off and I'll put them right back on, and then suddenly they're just reading gibberish. They no longer work. I'm not sure if it's something that I'm doing to the front of the mechanism where the screen is, or if it's something that's happening with the electronics. But they definitely seem to fail a lot more than I'd like. I'm going to probably switch to a laser rangefinder on on my larger robots. Here what you're seeing is I've put all of the electronic components for this robot on a piece of cardboard, and just kind of glued them down or tied them down, taped them down. And what I did that for was I like to put all the components I'm going to use together, power them, make sure everything works, make sure it fits in the form factor I need, make sure that I can wire everything and I don't have something like a lack of amperage or something that's not going to let a board run. So I test all of that before I actually make decisions about the body of the robot. Now here I cheated a little and I've already assembled the top, so you can see that my AIY package speaker and microphone are on top. And just like in my desktop kit video, you'll see I'm not using the Google Voice package. I'm still using Pocket Sphinx and Python and my own stuff. I don't want to use the Google Voice package because I want this to work well offline. Here I'm mounting a little display so we can do some debugging. We're probably going to put a better display on this, and maybe even a head. I have an idea for a head that can be on here, so he'll kind of have a body shaped a little bit like Wally, but in the sake of the theme of the thing, I'll probably give it kind of a domed head, maybe even a clear domed head with lights inside of it. And there we go. And this is the Kinect. It's not quite as good as some of the cheap laser rangefinders you can find now on Amazon, but I've got one of these laying around. I got on eBay for like $80, and it does give you a nice point cloud, so you can do ROS navigation with it. You still need the sonars because that Kinect is not good within a foot or two of the front of the thing. So when it gets close to a wall, it's like it's blind. So the sonars are still necessary for close-up obstacle detection, but the Kinect enables you to map a room in a way that is usable in ROS. So here's the completed robot all put together. I've done a little bit of decorating. I've got the Kinect on and working. Camera's giving me a video. The sonars are working. Let me show you a display of that in a second. I've had it rolling around, but it's on a very small area where I'm filming here. I'll get some videos moving around shortly, but here on the display, if I can get it to come into the picture, these numbers where it says mode 5, that's just sit on the desk mode. The W indicates how many turns of each wheel have happened, because those are the encoders being read by the Arduino. So as I turn the wheels here, you can see the wheel counter changes. And then these numbers down here indicate the sonar distances, and I'm just moving things in front of the sonars. So yeah, so the sensors are good, even the Kinect and the wheel encoders are good, and I've got everything powered here by this single switch. So I turn it on, it boots the computer, and this is the final wiring job, which I'll admit is a mess. There is all the parts you saw going in. I've got this Arduino Mega here. I've got the Raspberry Pi mounted up here on the top. And I've got the battery down here under this mess of wires. But I have leads that are coming out that I can throw a switch and then connect the leads to a charger and charge the battery. And that's about it all opened up. And the hinges that you saw me working on, these are a 3D printed hinge that I think I got off of Thingiverse. Honestly, if I can find a link to it, I'll post it. I didn't design those. They're a great design. They were definitely on Thingiverse. So yeah, so we should be able to see this robot moving around soon. It should be capable of the whole ROS navigation stack. So I'm hoping to have this autonomously navigating the house soon. Right now it already does obstacle avoidance, and the microphone and the speaker are working on that AIY board that I put up there. There's the speaker and the microphones. So yeah, it should be ready for ROS navigation stack soon. I haven't actually used that. My last large robot used a custom solution, which was not as good as ROS, so we're gonna switch to the ROS navigation stack now. We're calling this robot PiCard. That's Pi-controlled Arduino robot drone. I am a big Star Trek nerd, so we painted him in nice Starfleet uniform. I've given up one of my many badges for the project. And these are screws are just rank pips. There's no point to those. So I'm going for, I was thinking about calling him Locutus or PiCard, but I think PiCard Pi-controlled Arduino robot drone sounds better. So we'll go with that. Really happy with how the project is coming along. Can't wait to show everybody this rolling around the house.
So that's it. Please like, share, and subscribe, and let me know what you think in the comments.